Hello everyone, and welcome back. Today we are going to start talking about how to describe the motion of an object. Last time we talked about units for measuring distance and time and mass, but in particular distance and time, and what we're going to do is we're going to use those along with our ideas about numbers, significant figures, and things like that, and start talking about how to describe something that's actually moving. Well, before we start with moving, we'll talk about how to describe where something is. And we're going to start, this will bring us to section 2, motion in one dimension. Now, we start with one dimension for several reasons. Once we understand one dimension, it will lead much more easily into 2 dimensions and 3 dimensions. But also, there are many, many kinds of motion that can be described with just one-dimensional motion or one variable. Anytime you can describe the position of something basically with one variable, one number, one position coordinate, that is basically describing something in one dimension. For example, if you wanted to drive, say, from Atlanta to Chicago, which is about 720 miles or so, you really don't care what lane you're in as you get there. All you really care about is how far have you gone from Atlanta to Chicago out of that 720 miles or so. You know, are you at 100 miles or 300 miles or 570 miles, something like that. All you really care about is the distance that you have traveled from the beginning to your final destination. Where you are left to right is really inconsequential. So, when describing your motion from here to Chicago, you're really describing a motion in one dimension. It's not physically exactly to linear motion on a straight line, but it's close enough that that's all you really care about. So, that's what we're going to start with, motion in one dimension. To do that, we're going to start with describing where something is. And to describe where something is, we're going to need a coordinate system. So we'll start out by defining a coordinate system. Let's imagine that we've just got some line, and as I said, this could be a straight line, or it could be a meandering line along the highway, or a line along the sidewalk, or anything like that. Any coordinate that we can just use a single number to describe. Well, we want to start, we also need a point where we're going to measure our distances from, what we will call our origin. We'll label our origin as 0. And then motion to one direction we'll call positive positions. So let's just say 1 meter, 2 meters, 3 meters, something like that. And then positions to the other side will be negative values. -1 meter, -2 meters, -3 meters. Now there's nothing particular about one side or the other. By convention, we usually define positions to the right of the origin as positive and to the left of the origin as negative. But that is completely dependent on how you define your coordinate system. If we're facing this way, right is on this side, left is on this side. But if I'm, say, back here, right is on this side, and my right is on this side, my left is on this side. So it really doesn't matter. It's totally arbitrary. We'll just define one direction, and then we'll go from there. So here's our coordinate system. Now let's imagine that we've got some object, here's a little person, who's going to be going for a walk, going to be moving along our coordinate system. This person could be going one direction, in this direction, or could turn around, come back this way, could move slowly, could move fast, doesn't really matter. However this object is moving, they're moving along our one-dimensional coordinate system. Now, how can we describe where the person is? Well, very easily, we can say, oh, the person is at the 2 meter position, or the person is at the -1 meter position. When we usually talk about position, we usually use the coordinate or the variable r. With one dimension, that's kind of a very simple thing to do, so rather than just r, I'm going to just use the coordinate x. So I'm going to define our coordinates on this axis. I'm going to call this our x-axis. And then wherever our object is, so if our object is over here, our little person is here, I'll say that x equals 2 meters. Or if I want to be more precise, I might say 2.0 meters, 2.00 meters, how many sig figs I want. And then if the person is over here, then we can say that x is equal to -1 meter. Okay? Now, as the person moves, as our person moves along our coordinate system, how are we going to describe this motion? Well, one thing we could do is we could make a table. We could make a table of x values at some particular time. And then we can make a table that identifies where the person is at different times. Now, let's say that the person is at position 0, at the origin. Well, what's the time? Well, it might be 3:27, or it could be 12:05, or whatever. To make things easy, we're going to measure times using our standard SI unit of time, which is seconds. And we're going to imagine we start our clock at some specific time, our initial time, and we'll call that 0. And so let's just say at t equals 0, x equals 0. So that means that whenever we start our clock, our little person is at x equals 0. No, they don't have to start out at x equals 0. The person could start out over here. Let's just say that. Let's just say that when we start our clock, the person is at the position 2 meters. And then where is our person at different later times? We might say at 1 second, the person is perhaps still at 2 meters. At 2 seconds, the person is at 3 meters. At 3 seconds, the person is at -2 meters. So what's going on here? What does the motion look like? Well, at t equals 0, we know the person is at 2 meters. At t equals 1, the person is still at 2 meters. Now, does that mean that they stayed at 2 meters? Well, not necessarily. They could be at 2 meters and then gone somewhere else and come back. All this is telling us is that at time t equals 0, the person is at 2 meters. At time t equals 1 second, the person is at 2 meters. And then at 2 seconds, the person is at 3 meters. And then 1 second later, the person is down here at -2 meters. So this table sort of way of describing motion is one way of describing it, but it's really just describing the position at specific times. Another way that we might describe motion is to have an equation that describes a relationship. So we might say that x is a function of time, and it equals to, let's say, 1/2 t squared. So what does this mean? Well, we could fill out a table using this. We could say then, again, we could make a tx time. When t is 0, we put in 0. 0 squared is 0 times 1/2 is 0. X is 0. When t is 1, 1 squared is 1 times 1/2 is, I'm going to write these now as decimal, 0.5. When t is 2, 2 squared is 4. 4 times 1/2 is 2. So this would be 2. So you could say 2.0. When t is 3, 3 squared is 9. 9 times 1/2, 4.5. So we'll say 4.5. So this gives us a table similar to the other table, but in this case, if we wanted to know where the person was at, say, 0.5 seconds, we could put that in here. At 1.37 seconds, we could put that in here and figure out what the position is. So this gives us a much more complete idea of what the motion looks like. But let's be a little bit careful. I've been very sloppy here with units. What are the units here? Well, we like to write time in seconds and x in meters. So we need to make that clear here, that if t is in seconds, we get x equal to meters. So we need to put some units in here. We need to cancel out our seconds squared and then multiply by meters. So we'll have 1/2 meters per second squared times t squared. Then if we put in, say, t equals 2 seconds, 2 seconds squared is 4 seconds squared. The second squared cancels. We have 1/2 times 4 is 2, but now it comes out as 2 meters, so these would all turn out to be meters. So that's good, that's good. Make sure you have the appropriate units. If you're going to have an equation, make sure you have the appropriate units in the equation so that the units work out the way you want. Here I've emphasized that x is a function of t, very, very much like you might write something like f is a function of x. But I'm going to typically not write that, and we'll just keep in mind that x is a function of t. X is a variable that is changing as our little person moves around on the x-axis. X is a function of t, but I will just write it as x. X and then equals, say, something like this, or in a tabular form like this. Okay. One of the easiest things, and also one of the very important things that we can use to describe motion is the speed. How fast is something moving? So how fast? Now we might refer to this as speed. What is the speed of the object? The speed we'll define as the distance traveled over the total time. Whoops, total. So, for example, let's imagine that our person goes from -1 to 3. So let's imagine that x goes from -1 meter to 2 meters in, let's say, a time of, we might say, 2 seconds. So make this -0.1 to 2.0. So what's the speed in this case? Well, we've got a distance of from -1 to, that would be 3 meters. So this would be 3 meters over a time of 2 seconds. This gives us a speed of 1.5 meters per second. So the units that we find for speed are meters per second. Now, okay, that's good, but we need to be a little bit careful here. In going from, let me rewrite this, I was very messy about that. So let's say from -1.0 meters to 2.0 meters. Now let's be a little bit careful about this. The person starts out at -1 and then goes directly to 2 meters. Now if that's all the motion, if that's exactly what the motion looked like, then the distance traveled really is 3 meters. But what if the person came over this way and then came back and then moved around and then ended up at 2 meters after a total time of 2 seconds? Well, then the distance traveled will not just be 3 meters. It will be some amount and then some more and then more this way, this way, this way. The distance traveled in that case would be much more than 3 meters. We're going to define a quantity that really only depends on the value of x. This quantity is what we call velocity. The velocity we will define as a very, very important quantity that's called displacement over the time interval. The displacement we will write as delta r, or as I said before, because we're only doing this in one dimension, I'll just call this delta x. And then divided by the time interval, which is delta t. Now I'm using a symbol here, the Greek letter delta. It just looks like a triangle. It's actually a capital delta. A lowercase delta looks something like that. But in this case, it's a capital delta. I'll just typically refer to it as delta. This is going to be a kind of a symbol that we will use very often, over and over again. Whenever we take delta of something, like delta x, that means the change in x. So whatever the delta is that you're taking, delta x, delta t, delta r, delta anything, what we mean is the change in that quantity. So delta x means the change in x. And what we mean by that is xf minus xi. In other words, xf, this is the final position. While xi, this is the initial position. Okay, these will be terms that we will be using again over and over.